All right, so we just did the remainder theorem. We're now going to use the knowledge from the remainder theorem to do something called the factor theorem. And again, we're setting ourselves up because we want to know how to factor big, long polynomials. And the remainder and factor theorem will do that. So we have the factor theorem written here. It says x minus a is a factor, and then we have this IFF, f at a equals 0. I can tell you that this IFF means if and only if. Oops, I don't need two F's now. If and only if. This is a short version or short form that mathematicians will use to describe a biconditional statement. It means that this theorem works in both directions. So the theorem as it reads would say if x minus a is a factor, then the remainder is going to be 0. But the opposite is true. So if the remainder is 0, then x minus a is a factor. So it works in both directions, but instead of writing it down twice, we can use this IFF shortcut to tell the reader that it works in both directions. So we're going to ask this question and use the factor theorem to find out if a certain factor or a certain binomial is indeed a factor of this polynomial. So we have a nasty divisor here, but we're still going to use the remainder theorem to test the factor theorem. So the way we do that is say, hey, guess what? I want to know if this is a factor. So I'm going to sub in the root and see if I get a remainder of 0. The catch in this one is the root's kind of nasty. What's the root? Can anyone see it right off the top? Bring the negative 3 over. 3 over 2. Is that fair? So the root is 3 over 2. So when we go and sub this in, it's actually going to be a little nasty. So we're going to sub it in. So wherever we see an x, we're going to have to put 3 over 2. Now we're going to have to do some pure math. Now if you really were struggling, you could use the decimal 1.5, but I think we can do the pure math. When we cube a fraction, we cube the top number and the bottom number. So when we cube 3, it's 27, and when we cube 2, it's 8. Minus, and then you see it's minus x squared, so you just square it and then you subtract your answer. When you square a fraction, you square the top number, which is 9, and you square the bottom number, which is 4. Here, we're going to multiply by 7. So we know that's a fraction, 7 over 1. And when you multiply fractions, you multiply the tops, which is 7 times 1 is 21. And you multiply the bottom, which is 1 times 2 is 2. And then we just have an add 6 here. I can simplify things a little bit easier by dividing both of these by 2, and I get a 1 and a 4. So 2 divided by 8 is 1/4, so I can reduce that. So I actually end up with a fraction 27 over 4. This I'm going to leave as minus 9 over 4. I'm eventually going to have to add and subtract these, so I'm going to get a common denominator and change this one into over 4 as well. So I had a 2, so it changed to a 4, so that meant I multiplied by 2. So I have to multiply by 2 up top. And this one I'm going to change to a fraction out of 4 as well. So it's 6 over 1. Change it to something over 4. Well, that's 24. 24 divided by 4 is 6. And now, since they all have 4's in them, I'm going to add the numerators. So I got 27 minus 9, which is minus 36. Oh, sorry, 27 minus 9 minus 42 plus this negative 24 plus 24. I have people checking. I think it's 0 though, isn't it? Yeah. So 0 divided by 4, of course, is just 0. So it turns out when we plug this in, we actually got an answer of 0, which means what's the remainder? 0, which means it was a factor. So therefore, 2x minus 3 is a factor. Now, I know that was a little nasty with the fraction, but the concept is still there. We may not end up always with fractions, but we will get ones that we can figure out. So this is going to be one of our first steps when we actually need to go off and factor these big long ones, is to try and use the factor theorem and the remainder theorem to find an actual factor. Then we can go off and go the next step. Any questions on the factor theorem? Okay, and this last question that we're going to do is an example where it's just getting us to practice the factor theorem in a different sort of question. So it says when x cubed plus 2x squared minus kx minus 12 is divided by x minus 1, the remainder, it turns out, is 20. So I want you to tell me what this value for k is in there so that you would get a remainder of negative 20. So what I'm going to do is ask you guys to work for, we'll pause the video for a second and work with your elbow partner. Try this, try fiddling around, and then we'll come back and listen to the second half of the video and see what it is. Okay. Now that you've had a chance to try it, we're going to go here and say, look, it says I've got some polynomial and it's divided by x minus 1. That means if I put in the root, which in this case is an easy root, it's just 1. So if I put in 1 into this polynomial, the answer apparently is going to be negative 20. So if I put the 1 into the equation, so instead of x cubed, it's 1 cubed plus 2x squared, so 2 times 1 squared, minus the k, I don't know that, but if I put in the x equals 1, minus the 12, if I put in the 1, this question is telling me that the answer is negative 20. So now I should be able to go along and do the math and figure out what the k was to get me an answer of negative 20. And luckily the numbers are nice and easy. So it's 1 cubed, which is 1, plus 1 squared is 1, times 2 is 2. 1 times k is 1k, but it's a negative 1k. Minus 12 equals negative 20. I'm going to have minus k on this side. I got negative 20 over here. I'm going to bring everything over, so it's going to be a minus 1, a minus 2, and a plus 12. You may choose to reduce it before you move it over. That's totally fine. Negative k is negative 11, I think I get. And I don't want negative k, I want positive k, so I divide both sides by negative 1, and I get k equals 11. So it turns out that's that missing magic coefficient that when it's divided by x minus 1, it's going to get a remainder of negative 20. Okay? So this is just getting used to these two theorems. These two theorems are going to be your first steps of doing huge factoring. And the huge factoring is what we're going to do next time I see you. So if you want to practice, you can practice 176, numbers 1, 2, 4, 5, 9, and 10. Again, as I said, these are quite a few questions. I don't expect you to do all of them. But do at least one like this example 3 with a k, because they'll probably ask you to do something like that. The other ones, it's just a matter of practicing the remainder and factor theorem.